Here we go on the second part of today's class. So once again, just make sure that we're all on the same page. This is where the material for exam 2 begins. All right, so we're going to have to start on, we're going to have to continue on in this summer course. We're going to talk about probability right now, but everything from here on out is going to be on exam number 2. So we are getting very, very close to the point where we can actually start to analyze some actual data from scientific psychology experiments, from clinical interventions. We just have a little bit more work to do. All the pieces are coming into place, but we just got a little bit more work that we need to do. So we're going to continue with that analogy of this journey where you're learning all these skills, and today we're going to be painting the fence. But we're going to start peeking at what it is that we're going to be able to do and why statistics is so important for psychology. So I'll start off with an example here. So let's say that you graduate from IUSB and you start working with individuals with different learning needs. So let's say that you work with autistic children. And you have a class where you teach autistic children. And in your class, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 students in your class. And because of your psychology training, you determine a new way of teaching these students. So let's say that you develop a new program that takes advantage of interactive tablet technology, and you devise a new learning program for these students. And you measure their learning abilities before the treatment. You then measure their learning abilities after the treatment. You measure their learning outcomes. And let's say that it's a resounding success. Let's say that these students learn more than they ever did before. This new treatment is a resounding success for these particular students. Without the skills that we're learning in this course right now, without the skills that we're learning building up to inferential statistics, this resounding success for these 14 students is where your story ends. Because even though you have this wonderful treatment, even though you have this wonderful intervention, without inferential statistics, all that you can say is that it works for these 14 students right here. And if that was all that psychology can do, then psychology would be extremely limited in the people that it can help. And let's face it, it would be reserved for the very wealthy. The very wealthy individuals would have their own personalized psychologists studying them and making sure that they're okay, with no ability whatsoever to generalize to the population and help millions of people. So just remember that when we're going through this next phase where we start to introduce inferential statistics and hypothesis testing, the skills we're working with are what allow us to take a result like what happened with these 14 students and generalize it intelligently so that we can apply it to the population of students. So if we find out something that works for 14 autistic students, with inferential statistics, we can intelligently generalize and help autistic students from around the world. So we can help this child, this autistic child here, these 2 autistic children in a music program, this child who is showing that classic cup stacking behavior that autistic children often display. We can help this child that is showing that isolated play that oftentimes happens with autistic children. We can help the population of autistic children. So again, bear that in mind, how much more useful psychology is, how much more impactful psychology is because of the skills that we're learning here, where we can intelligently go from 14 subjects to the population, in this case, of individuals who have autism. Because again, without the skills we're learning in this course right here, all that we could say after this resounding success is that it works for these 14 students. And if somebody came and said, you know what, my child is struggling at school, my child suffers from autism, do you think, your intervention will work for them? Without inferential statistics, all you can say is, I don't know, maybe, maybe not, who knows? It works for my 14, that's great, but I don't know if it'll work for anybody else. With inferential statistics, you can generalize and say, yep, it worked for my 14, it'll work for the population of autistic students, and that's how you make powerful impacts in psychology. So that's what we're working towards. So keep that goal in mind, and we're going to keep filling in the little missing puzzle pieces. And the next puzzle piece that we need is probability. So we're going to introduce the idea of probability. This is something that you've probably already studied, but we're going to switch it up a little bit and think about it like statisticians think about probability. It's a little bit different. You've been taught the math probability. We're going to take a look at statistics point of view with probability. We're going to tie this into frequency distributions, and that's the goal for this hour of the course. All right, so introduction to probability. So, for any outcome, for any series of outcomes, the probability of a particular outcome occurring is the possible successful outcomes divided by all possible outcomes. So that's the original mathematical definition. So for example, if you're flipping a coin and you win when heads is flipped, the possible successful outcomes, there's one successful outcome, right? You win when heads is flipped. The all possible outcomes, there's two possible outcomes. It can come up heads or it can come up tails. So we have 1 divided by 2, and that's why the probability of flipping heads is 50%. It's 1/2, 50%. That's where we calculate these probabilities. Probability is so incredibly important in statistics. It gets its own symbol. Once again, that idea of foreshadowing. And its symbol is P. So P stands for probability. And if you've talked to psychologists that do research, you will know that the p-value is one of the most important concepts, one of the most important things that we try to determine. That'll come up more and more as we go along, but p-value is an incredibly important idea in statistics, and you will see psychologists talking about their research and saying things like, oh my gosh, my experiment, what a success, p-value less than 0.05, it's amazing, I got significant results. And you'll also hear them saying things like, well, you know, I didn't find anything this time in this experiment, p-value greater than 0.3, well, back to the drawing board. A lot hinges on this p-value, this probability. So the thing to think about is that for a statistician, probabilities are equivalent to proportions. So when I talk about probability, try to conceptually think of a proportion, a piece of something. And what that something is a frequency distribution. So for a statistician, probabilities, we don't think of them in terms of decimals, we don't think of them in terms of percents. We, at our core, think of them in terms of pieces of a frequency distribution, proportions of a frequency distribution. So let's get into just a little bit more terminology, just because you might see these mentioned somewhere and I want to make sure you know what they mean. So if you have outcomes that are classified as in different ways, so you got A, B, C, or D, right, and so on and so forth. So for example, rolling dice, right, you got an outcome of 1, outcome of 2, outcome of 3, outcome of 4, you got multiple outcomes. The probability of in brackets A means the probability of A occurring. So if you got probability A, or its short form, P of A, don't read that as P of A, read that as the probability of A occurring. And the probability of A occurring is a number of outcomes that are classified as A. It's mentioned in that way in case you have a broad number of different actual outcomes that can be classified in a single outcome. So for example, passing a course, your outcome could be A plus, A minus, B plus, B minus, and so on. All of those are classified as passing your course. And then is divided by the total number of possible outcomes. So that's just to kind of make it explicit in terms of this is some of the terminology that you might come across when you're reading your textbook. Importantly, however, once again, probabilities are equivalent to proportions. Proportions of pieces of a frequency distribution. All right, so probabilities and frequency distributions. We're going to illustrate this by taking a look at the outcome of die rolls. So we're going to start with one, we're going to build up to more than one. And probability and frequency distributions, what they did to figure out a lot of these probabilities and build up these frequency distributions is what's known as a Monte Carlo experiment. And a Monte Carlo experiment is literally when you just do something over and over and over and over again to see what is the probability of a certain outcome. So this is named from the experiments that were done at the Monte Carlo casinos. When people were interested in probabilities, they were interested in the probability of roulette, they were interested in the probability of blackjack, all those games of chance, and the mathematics just wasn't there to calculate what those probabilities were. They didn't have computers back in those days to simulate what those probabilities were. So they literally went to the casinos with pads of paper and just made notes of how often people won, how often people lost, and then just used those numbers to tabulate these probabilities. So if we did that with die roll outcomes, if we went to Monte Carlo and just saw people rolling single dice and saw what came up, we would have certain outcomes and they would have a certain frequency. So the outcome of rolling a 0, so if we're talking about 6-sided dice, the outcome of rolling a 0 would have occurred 0 times, right? So that's not a possible outcome. That would have occurred 0 times. Let's say that we stayed there for a long time, and we might have noticed that a 1 was rolled 921,541 times, right? So we recorded that many. A 2 was rolled 1,042,312 times. A 3 was rolled 921,825 times. And so on and so forth. A 6 was rolled 1,056,423 times. A 7 with a single dice, never rolled. You can't roll 7 with a single 6-sided dice. So those are the frequencies that we might have observed. This is the actual frequencies. In the long run, you get to a certain ratio of frequencies, and they're a little bit easier to deal with. So you'll notice that all of these are very close to 1,000,000. So we can just take out that 1,000,000 from each of those. We can just divide it by 1,000,000, and we'll end up with what's known as your expected relative frequencies. And these expected relative frequencies are the proportions you can expect in the long run. So if you have a fair die and you're rolling it over and over and over again, you should get, on average, out of 6 rolls, you should get 1 roll of 1. You should get 1 roll where you get up with 2. You should get 1 roll where you end up with a 3, 1 roll where you end up in a 4. In the long run, for a fair die, these are the outcomes that you can expect. Simplify, just scale down so that we don't have huge, gigantic, horrible numbers to deal with. All right, so far so good? Okay. So those are the numbers. This is you might hopefully remember, that's a frequency table right there. And we can calculate the probabilities of rolling any one of these numbers by using the formula that we just introduced. So we can calculate these by using the formula for the number of occurrences divided by the total number of occurrences. The number of a specific occurrence divided by the total number of occurrences. So if we were playing a board game like Snakes and Ladders that had 1 single dice, and we wanted to know what's the probability of rolling a 0 in this game. Well, the probability of rolling a 0 is 0 because there is 0 outcomes that are classified as 0, and you divide that by the total number of outcomes, which is 6. 0 divided by 6, that's 0. You got a 0% chance of rolling a 0. What if you need to roll a 1? What if you are 1 away from winning that game? You're 1 away from the finish spot, and you have that rule where you got to roll exactly. You got to roll the exact number to get into the finish spot. You got to roll a 1. What's your probability of winning on the next turn? Well, there is 1 outcome, right? Frequency of 1, where you'll win. There are 6 possible outcomes. 1 divided by 6 is approximately 17%. So you got a 17% chance of winning on your next turn. If you need to roll a 2, there's only 1 outcome of rolling a 2, 6 possible outcomes, 1 divided by 6, again, 17% chance. And really, whatever number you need to come up you have a 17% chance that that number will come up. And then you see there's no way of winning when you have to roll a 7. So those are the probabilities, those are the mathematical probabilities. That's the way that a mathematician would come at this particular analysis. What about a statistician? Well, a statistician will take these expected relative frequencies and they'll put them into a frequency distribution. So here we have a frequency distribution where we got the possible outcomes and then we have the frequency with which they're expected to occur. And notice that 0 has no bar, 0 is not expected to ever occur. A 1 occurs with a frequency of 1, and a roll of 2 occurs with a frequency of 2. Roll of 2 occurs with a frequency of 1. 3 occurs with a frequency of 1, all the way up to 6. And you'll notice that it's a flat distribution, indicating that the frequency of each outcome will occur at the same level, the same frequency. So that is the frequency distribution version of this. So let's take a look at how this can be used to answer some questions, some probability questions. All right, so once again, let's say that you were playing Snakes and Ladders and you needed a 2 to win. You have to roll a 2, that's what's going to win you the game. What's the probability that you're going to win this particular game? Well, we calculated out the probability of rolling a 2. That's 1 divided by 6, that's 17%. You got a 17% chance of winning on your next roll. That's the mathematical way of solving it. Statistical way, proportions of a frequency distribution. There's your frequency distribution of all the possible outcomes. Where's the outcome where you win? It's that bar right there. And that bar is 17% of the entire distribution. That blue proportion is 17% of the entire distribution. So if we can figure out the area of that blue bar, we can figure out that we have a 17% chance of winning on our next roll. So that was pretty straightforward, that was pretty simple. The power of this comes when things start to get not so simple. So let's say, for example, that you were playing a game and the rules of the game were that if you roll an even number, you win the game. What's the probability of you winning the game on the next turn? Well, we know that 2 has a 17% chance of occurring, 4 has a 17% chance of occurring, 6 has a 17% chance of occurring, but what about an even number? What's the probability of an even number occurring? And this is where it can start to get complicated, because the question comes up as, what do we need to do with these numbers? Do we add them all up? Do we multiply them? Do we raise them to the exponent 3? Do we divide by 3? What do we do with these numbers? What do we do to find out the probability of getting an even number? It can start to get a little bit complicated. Take it to a frequency distribution makes it a lot simpler. So once again, we think about we need to roll an even number. Where is it that we win? Well, we win if we land in those blue bars right there. What's the proportion of those blue bars to the entire distribution? The blue bars are now half of the entire distribution. So we can very straightforwardly and easily figure out that we got a 50% chance of rolling an even number. So again, changing it into a proportion simplifies a lot of these calculations that we're going to be doing for statistics and psychology. All right, so far so good. Any questions? Okay, so let's make this a little bit more complicated. 2 dice roll outcomes. So now we're rolling 2 dice, and we're going to figure out probabilities for rolling 2 dice. So for rolling 2 dice, there's your expected outcomes right there. You can see that there's no way to roll a 1 when you're rolling 2 dice. There's only one way to roll a 2. So there's only one expected relative frequency of rolling a 2 because you got to roll a 1 on the first dice and you got to roll a 1 on the second dice. There are 2 ways to roll a 3. You can roll a 1 and then roll a 2, or you can roll a 2 and then roll a 1. There are 6 ways to roll a 7. The 7 is the most frequent outcome. The 7 is the mode for this frequency distribution, because you can roll a 1 and a 6, you can roll a 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, 6 and a 1, Those are all the ways of rolling a 7. And then we get all the way down here. You need double 6s, and only double 6s will get you a 12. And there's no way to roll a 13. So we look at the probabilities of these outcomes. And for the 2 dice rolls, once again, classified, the number of outcomes that are classified in a certain way, divided by the number of possible outcomes. There are 0 things that are classified as a 1, divided by 36 gives you a 0 probability of rolling a 36. There is only one way, one outcome, where you roll a 2, divided by the total number of outcomes of 36 equals 0.03. So if you are playing Monopoly, does everybody here know what Monopoly is, board game? If you're playing Monopoly and you land on Park Place, and you're able to buy Park Place, your chances of landing on Boardwalk to complete that, high-end retail space is only 3%. There's only 3 out of 100 times where you're going to land on Park Place and on your very next turn, land on Boardwalk. And we can calculate these out for every single outcome. So for example, here for a 7, there are 6 outcomes that are classified as 7, right? 1 and a 6, 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, 6 and a 1. Those are the 6 outcomes. 36 outcomes in total. You got a 17% chance of rolling a 7. It's the most common roll for 2 dice. So those are the probabilities that we've calculated out for rolling 2 dice. We can also take this frequency table and put it into a frequency distribution. And statisticians think about probabilities in terms of that frequency distribution. So let's take a look again at some of the ways that this can help us. Let's say that we were playing a weird game with a friend. They were really into mathematics, so they devised a game where you win if prime numbers are rolled. Those are the prime numbers right there, numbers that are divisible only by 1 and themselves. 1 is not a prime number. So anyways, we got 2, 3, 5, 7, and 11. We have their probabilities. What's the chance of rolling a prime number when you're rolling 2 dice? Once again, it can get complicated. What do we do with these numbers? Do we add them? Do we multiply them? Do we take the average of these numbers? Is that the probability? What do we do with these numbers? Can get very complicated, but if you put it into a frequency distribution, once again, we have the entire frequency distribution, which is all of the outcomes. We can then color in the areas, for example, in blue that we're interested in, where we win. Those are the areas right there. And then what we need to do is we need to simply find out what is the proportion of the blue part to the entire frequency distribution, and that will get your probability for calculating, for rolling a prime number. Now, you might be sitting there going, well, that was fine and dandy when we had a square for our frequency distribution, right? It was pretty simple and straightforward when our frequency distribution was simple and straightforward. But this is getting a little bit complicated. So how do we calculate the area of that blue section? We'll be getting to that because of a little math magic we're going to be introducing in just a little bit. But just bear in mind that there is a way. We'll show you that in just a bit. But right now, just concentrate on the idea that your probability equals a proportion, a part of your frequency distribution. All right, and let's take this up one more notch just to kind of show you what's going to happen. So 5 dice roll outcomes. Let's say that you're playing a game like Yahtzee where you got to roll 5 dice, and we have all of these outcomes here with their expected relative frequencies. So there's only one way to roll a 5. You got to roll all 1s. You got to roll 1, 1, 1, 1, 1. There is 735 ways to roll a 16. You can roll a 1 and a 3 and a 2 and a 4. I'm not going to go through the whole ones. But anyway, 735 ways to roll a 16. Different combinations for any different outcome. Only one way to roll a 30. You got to roll all 5 6s. What's the probability, what's the frequency distribution of these outcomes here? If we were to plot this frequency table in a frequency distribution, that's what it would look like. And notice that our frequency distributions now are starting to look more and more like that familiar bell curve that you might have heard before. And as it turns out, this curve here is something that occurs very often in nature. And this curve here is what statisticians have spent a lot of time studying and learning everything they need to know about that particular curve. So for example, if we were to ask ourselves, what's the probability of rolling 12 or less? The portion of the distribution we're interested in is that part right there. So we got 5, 6, 7, 8, 9, 10, 11, 12. That's the blue bars. Those are the areas. And by ourselves, it would be very difficult to calculate out what that proportion is. But statisticians have already done it. So all we need to do is figure out a way to find it, and we'll show you that in just a little bit. But that would be the proportion we're interested in, 12 or under, if we needed to roll 12 or under to win. If we needed to roll 23 or over to win, then that is the area of the frequency distribution that we're interested in. That is the proportion of the frequency distribution that we want. So if we needed total points, and we needed 23 or more to beat our friend at Yahtzee, that's the probability, that proportion right there, of the chance that we would beat our friend. That's that proportion of the entire distribution is the probability of rolling 23 or higher. And if we have a little bit of weirdness and we got to roll 23 or higher, or 23 or higher, or 12 or less, then that's the probability, that blue area right there. So as I mentioned, this type of a curve, this bell curve where there's low frequencies in the tails, higher frequencies in the center, this is something that just pops up in nature over and over again. Very importantly, pops up in psychology abundantly, right? Very, very often. And thankfully, statisticians like Gauss, statisticians like Laplace, they have already done all the calculations for this distribution. They've already figured this distribution all out. So all we need to do is understand that when we're looking at probabilities, we're looking at proportions of a curve, and we're going to lean on the fact that statisticians have already figured out these curves in order to get to the final answer. So the one thing I want you to take home and kind of get an understanding of is that probabilities correspond directly to pieces, proportions of a frequency distribution. All right, are there any questions on that kind of intro to probability? It's all good? All right, so that's where we're going to end the second hour. So don't forget, for the pretest points for Chapter 4, you still have the ability to do the MyStatLab study plan for the Quiz Me option. You're looking for those mastery points. We are now in exam number 2. So the pretest points for exam number 2 are going to be due right before exam number 2. So Chapter 4 is not due by tomorrow at midnight. It's due whenever exam number 2 is coming up. And it's 11 right now, so let's take a 15-minute break. And we'll start up again at 11:15. And we will continue on with this look at probability. So if you need to take a break, feel free. If you're working on other stuff and want to call me over, I will be happy to help.